I hope everybody is fine. And in this video, I'll try to talk about the correction of Bohr's theory due to the finite nuclear mass. And I would like to demonstrate here that how accounting of the nuclear mass into an atom led to the uh, discovery of led to the discovery of heavy hydrogen or deuterium. So, what we considered in the Bohr's model is an electron, and we didn't take into account the motion of the nucleus. Now, what we assumed here is that nucleus is infinitely heavy relative to electron. So it remains stationary while electron circulates around it. But actually, the nucleus has finite mass, and and both electron and nucleus, they actually revolve around their center of mass. So, to describe the motion of electron relative to this nucleus, we certainly should take into account the reduced mass. We should take into account the reduced mass. And let us assume that this reduced mass is symbolized as mu. And we understand that this mu is it is m by m plus m. So symbols have their usual meanings. This m stands for mass of nucleus, and small m represents mass of electron. Now, if we take into account this reduced mass in the equations of in the assumptions that were described by Neil Bohr, those equations will take a modified mathematical form. Like for centripetal force, we will have mu v square by r equal to 1 by 4 pi epsilon naught, then z e times e by r square. So to account for this spatialate, we are using the reduced mass of the system of hydrogen having a positively charged nucleus and the negatively charged electrons. So this will automatically lead to the energy in the nth orbit. Energy in the nth orbit of a hydrogen atom. If I go down to hydrogen atom, for which Z is equal to 1, this will give us that En is it is minus R Hc by n square. Now, what will be different in this equation is the value of this Rydberg constant, because this if we go back to this Rydberg constant, we have to manage m by reduced mass. So if I write down this Rydberg constant, this is going to be mu e to the power of 4 by 8 epsilon naught square ch cube. Now, where this mu is already defined as the reduced mass, so mu will be m by m plus m. Now, if we account for this, if we substitute this mu in this equation, in the equation for Rydberg constant, what will we get is this R is it is m e to the power of 4 by 8 epsilon naught square ch cube times m by m plus m. Okay, this m I have got out. So what we observe here is that we have a Rydberg constant, which is not exactly the Rydberg constant that we have had when we took into account the motion of electrons alone. And here, if I presume that Rydberg constant to be Rx, and if I define this R now, if I define this R now again, what will I write is R is Rx times m by m plus m. Now, what do I get from here is that this R that we will have, it's less than this Rx. Because we have incorporated the mass of the nucleus, right? So I can accordingly write down the wave number, and what would I conclude from there is I can say that this R is less than Rx. That means the wavelength, the lambda, if I write down the wave number that we have already calculated, what's that? That is this new bar, which is basically the reciprocal of wavelength. It is R times 1 by nf square minus 1 by ni square. Okay, so this is it. Now, what do I conclude from here is that this R is it is less than that of this Rx that I defined previously. So if this R is less than Rx, then this lambda will be greater than this lambda x. So there must be the shift. There must be there must be there must be the movement. There must be the shift in the spectrum that we are looking for. So what am I trying to tell here is that the spectral lines will be shifted, and they will be shifted towards increasing wavelength side. If we take into account the finite mass of nucleus, which is extremely large in comparison to the mass of the electron. Now, as Rydberg constant, this R, it depends upon the mass of the nucleus. Therefore, it's a constant for a particular atom. It cannot be generalized. The Rydberg constant cannot be generalized for every atom in reality, because it will act as constant for a particular atom, and every atom has different mass. Every different atom has different mass in nucleus, and varies slightly from atom to atom. So that variation may be extremely small, but there is variation. So this R cannot be strictly confined as a universal constant. No, it's a constant for a particular atom. Now, this variation that I was talking about, this variation of Rydberg constant with mass of the nucleus, this basically led to the discovery of heavy hydrogen. Now, this heavy hydrogen is also called as deuterium. This deuterium is an isotope. It's an isotope of hydrogen, having a mass exactly double, having mass exactly double than that of the ordinary hydrogen atom. So hydrogen atom and deuterium, the heavy hydrogen atom, this has a mass double than that of this hydrogen atom. Therefore, this Rydberg constant for deuterium is slightly greater than that of the hydrogen, right? So consequently, the wave number of the spectral lines that we will see for deuterium, they are slightly greater, and the wavelengths are slightly shorter for those corresponding to deuterium atoms in the spectral lines of hydrogen. So then finally this deuterium spectrum, it was photographed by Urey in 1932. And what he did, he photographed the hydrogen spectrum and observed that each hydrogen line was accompanied by a very faint line on the shorter wavelength side. And he measured that wavelength difference and concluded that this faint line was due to some isotope of hydrogen, and this isotope is commonly now known as heavy hydrogen or deuterium.